Yeah, thank you. So, good evening, everyone. Myself, Vinija Katale. As a part of this email, I would like to welcome you all to our 14th weekly webinar. I'm really thankful for our audiences, our subscribers, and our followers. You've been really supportive. It encourages us to keep going. Also, special thanks to the speaker community who's been really supportive. So, let me share my screen. So, this Mumbai is a Stanford initiative happening at global level. We arrange conferences on ML, AI, and data science considered with women, which has been spread across 150 plus cities, 60 countries, reaching 1 million plus participants worldwide. The first global chapter began in 2018. Our agenda is inspire, educate, support to all women in data science, data analytics, statistics, mathematics, machine learning, and artificial intelligence. Uh, these are the ambassadors of our rich Mumbai, and this is the volunteers and team members committee of the rich Mumbai. So Rich Mumbai started in 2018 in India with 8 speakers. Then we had conference in Vijay Family with 9 speakers. And since we were not able to hold offline conference this year due to this pandemic, so we started our YouTube online weekly webinar series and had 13 great speakers with us till now. So these were the topics that are covered in webinars in May and June, and these are the 4 along webinars in July. So you can connect to us through these platforms with Rich Mumbai. So our today's topic is handling bias in AI models using adversarial learning. So this will be delivered by our today's speaker, Debasmita Das. Hi, Debasmita.
Hello, I'm Vinuja.
Let me give a small introduction about her. She is currently working as a senior AI specialist in the AI research team of Mastercard. She has over 5 years of professional experience in the field of NLP and data science, and has previously worked with organizations like JP Morgan and ESPN. Also, I would like to mention that Debasmita is also the organizer of Women in Machine Learning and Data Science Mumbai. Uh, they were one of our first partners. We are very grateful for their support. So, let's start with the session. Over to you, Debasmita.
Thank you, Vinuja. So, hello everyone. So, my topic today is how to handle bias in AI models. So, first, I'll give a short introduction of what is bias. What do I mean by bias? Some examples in real life scenario which has been affected because of the presence of bias while training the AI models, and then we will talk about what are the difference fairness matrix and how do you mitigate it using adversarial training. So set the context. Let me give one example. This is an example of Amazon when Amazon started training its recruiting tool, which is like they were creating this tool that would help them in their candidate selection process. So what happened when they started using it? It was seen that the AI recruiting tool was highly biased against the woman. So it's like it was giving more score to the male candidates over the female candidates. So why was this actually happening? So this was happening because this has happened because of the bias which is present in the data which is used to train this AI model. So this happens with the historical bias. So what happens, so here in the right hand side you see there are two graphs which actually shows the difference between the male employee is to the female employee in the big firms, in the big technology firms. And we see like in technology roles the percentage of female employees are really less as compared to the male employees. So only because it was training its AI model on this biased data, it was by some means learning that okay, if you are a male candidate, you have a higher likelihood of getting selected, and if you are a female, you have a lower likelihood of getting selected only because their workforce is not balanced. So, what was actually happening was Amazon system taught itself that the male candidates were more preferable given its ratio of male and female in the company. Also, it was seen that it was penalizing the resume. So it was not like they were actually using the gender as a variable, but there were words which were already present in the resume of a candidate, which are good enough to indicate whether the resumes are of a male candidate or a female candidate. So what it was doing, it was penalizing the resumes which had the words like women's, like we write like captain of the women's club, or captain, like here captain of the women's chess club. So whenever it was getting such words like women's or like girls team, it understood that they were okay from these are resumes from female candidates, and it was penalizing it. So the scores given to a male and a female candidate of same qualification, the female candidates were getting a little lower score. So so this is like one of the examples which like a presence of bias in the AI model can cause harm to in the decision making process. So, going to the second example. So, this is again an example of Facebook. So, Facebook, we know whenever we open Facebook, we see advertisements related to maybe what we are searching, or maybe something even unrelated advertisements. So as most of the advertisements are based on what we are searching on the internet, and like based on what I'm posting on Facebook who are my friends. So there was an allegation against Facebook that Facebook was discriminating while showing advertisements for houses, all the housing related ads. It was taking into account the race, color, natural origin, and also religion of the person, because whatever we post in Facebook, like it based on our content and like maybe the pages we follow and everything, it's very easy for the Facebook team to figure out what race, color, or maybe the national, maybe the region where this person is from. It's like so. Based on that, it was there was this allegation that it was preventing certain people from certain community to view certain house related ads. So it was presuming that the the capacity to spend on a certain housing is it's like directly related to race and color. So it's again because of the bias. Maybe the history shows that maybe a certain community is spending more on housing than the other community. Based on that, you prejudice on your future decision making. So coming to my third example, here I see bias in facial recognition. So here what is, so I am referring to this paper which is called as Gender Shades, Intersectional Accuracy Disparities in Commercial Gender Classification. So this person is a graduate from MIT. What she is doing, she wanted to see. So it's there is a very interesting TED talk by this person. So here, so she's a black woman, and she is trying. There's this AI machine, and it recognizes whenever you it recognizes like facial expressions, like whenever you come in front of that machine. But it's like whenever she was coming in front of the camera, it wasn't able to identify her face. So from that, it triggered that there has to be some kind of bias in the way the facial detection algorithms are being tested. So what she did, she took different picture. So here, as you see, we she's dividing it into like fair skinned male, fair skinned female, dark skinned female, and dark skinned male. And surprisingly, what we see that all the classifiers are performing worst on darker female faces. They so there the error rate is above like 30% as an average. So most of the time it is getting anyone who is a darker faced, it is tagging them as male instead of female. So these are the examples of different kind of like some of the biases that can be present when you are training an AI model. So let's see, why do we face such kind of bias? Like what is the sources of bias? One, first is insufficient data. We know the data set, most of the data sets that we get are very imbalanced. If we have, like, let's see the example of the Amazon hiring tool. There, most of the data was for the female candidates, and the Y percentage of resume which was for the most of the resumes were for the male candidates. The percentage of resume for the female candidates were really really less than the male candidates. So when I have a very imbalanced data set, it for the minority group we start seeing a bias when we train it. Second is data collection. So even though we have a huge data set, sometimes we see for certain categories, we have a lot of missing values. So let's say the minority groups, or for let's say a variable which has five categories of which two are minority, maybe they do not have data available for few of the features, which again makes it difficult to take a very accurate decision for the minority groups. And the third is historical bias. This comes from human prejudices. This, like in hiring, like maybe hiring from only certain colleges, or more like a loan discrimination. So we do have very strict policies now against loan discriminations, which are being always like audited if there is some discrimination happening or not. But if we like maybe look at history or maybe like judicial sentencing, we'll see that okay, the black people are having a higher percentage of getting convicted than the white people. So all this because we train our data on historical events. All this three, all these three like bring in biases while training our model. So one thing which might be a question, like all these variables like race, color, religion, gender, which actually create this kind of issues, like which brings in the question of fairness, whether like in hiring both the male and female are given the same kind of opportunity or not. Like while approving a loan, whether people from all the different communities are given same like a same kind of like they like if you're qualified, like you should have the equal probability of getting a loan. So one of the naive approach can be, why don't I just remove all these variables from my model? I just do not include variables like race, color, religion, or gender into my model. Then maybe the model won't be able to figure out what is the color of this person or what is the gender of the person in case of maybe when you are doing a regime selection model. Now this is termed as like a fairness through unawareness. So it's like I am trying the machine not know about this variable so that it can start acting fairly. Now the problem in here is, even though I remove these variables from my model, there are n number of other variables which has the capability to tell the model that, okay, so let's say take the example of resume. I didn't have to tell the model that whether you are a male and female as a variable to identify that the resume are for a male and female. There can be words, maybe the way the female candidates write a resume can be different than a male candidate write the resume. I'm not talking only about the gender terms, maybe also the way of writing, the choice of words can also give a very good indication of which gender this resume belongs to. The same maybe in the case of loan. Depending on maybe HPI index or unemployment rate, or there can be so many macroeconomic variables which can give a very good indication of what is the gender, what is the race or the region from which this person belongs to. So, okay, so we have to figure out some ways other than like just removing these variables from the model. So let's first try to learn what are the different measures of fairness. So we train a classification model. We want to see whether my model is giving fair output or not. So here I'll be talking about three different measures, which is demographic parity, equality, equalized odds, and equality of opportunity. So some one term which I will refer in this presentation multiple times, which is protected variable. So protected variable is nothing but, let's say, a sensible variable like gender. So I am calling that as Z, but also like a protected variable because I'm protecting it because I don't want the gender to cause any bias in my output. So I have my input variables or my feature set X, and I have my model like which is fx, and I am predicting the output variable Y. And I want that my output variable Y should be unbiased with respect to Z, which is my protected variable. Let's say, for example, it can be race, gender, color, anything. So, what is demographic parity? So once these are so now these three are the three measures of fairness. So demographic parity tells that a predictor y cap, so y cap is my model is predicting y cap, satisfies demographic parity if y cap and z are totally independent. So this actually means, let's say z have two different categories, z equal to 1 and z equal to 2. So the probability of y is equal to 1 should, given z equal to 1, should be equal to probability of y equal to 1 given z equal to 0. So it's like so yeah. Now what it says, so what does it mean? It's mean that let's say male and female, the probability that a male qualified person will get selected is 50%. That's okay, not like qualified. So like the conversion rate of female candidate is 50%, and the same with the conversion rate of male candidate is 50%. It doesn't take into consideration that whether it is qualified or not. So now what it says, it doesn't really ensure fairness because that's what I just said. So doing so in demographic parity, what we do, we just say you have to select, if you select X, like X percent from one demographic parity, you have to select X percent from the other demographic. So in doing so, even if one one category of protected way, so like if z is like 0 and 1, let's say if one has less number of qualified candidates, just to ensure fairness by the terms of demographic parity, I have to select candidates who are not qualified at all. So that what it says, it cripples your utility. So it's more like, if I think about, I have to select only the qualified candidates just to make sure I am ensuring fairness in terms of demographic parity. I am selecting unqualified candidate from one demographic category. So coming to the second one, so it is equality of odds. So, what is equalized odds? So, it was formally defined in Equality of Opportunity in Supervised Learning. So, this is a paper, this is like a very good paper which first defines what is equality of opportunity, which takes care of the drawbacks of demographic parity. Here says that the definition goes like this, that the predictor y cap now satisfies equalized odds with respect to the protected variable, which is z, like, or a, like z and a, like it's the same. If output y, so like if your output and a are independent conditional of y. So okay, it's a very confusing way of writing. Let's look at what is written down. So it actually means when your outcome, sorry, when your actual y is 1, then the constraint requires that the predicted y has equal false positive rate across both the demographic. And the other way around, when your actual y is 0, the constraint requires that it should, your predicted y should have equalized false positive rate across different demographics. So here I just give the definitions of what is a true positive rate and false positive rate. Like we all know, like what is the definition. So just, it will be more clear if we go through some of this within this example. This so what does it say? Okay, so I have two demography. So let's say 100 from L and 100 from B, and we do see that the Lilliputians applicants have a 90% qualification rate, where the other type of applicants have a only 10% qualification rate. So we see that anyway this is like highly biased. But if you look at, let's say, a model is trained and we get an output like this, we see the percentage of qualified students admitted is 45 out of 90, which makes it 50%. And my percentage of unqualified students rejected is 8 by 10, which makes it 80%. And the same for the other kind of demographic, we see my false positive and true positive rates are same, which is like 50 and 80. So what do we see here? My equalized order is satisfied only because both the demographic students now have a 50% chance of being admitted if they are qualified, and they have an 80% chance of being rejected if they are unqualified. Now, demographic parity here is not satisfied because we see that 47% of demographic 1 students are being admitted and only 23% of demographic 2 students are being admitted. But that is fine over here because we have made sure that whoever is qualified enough do have a 50% chance of getting admitted. And if you are not qualified, irrespective of your demographic status, you will have an 80% chance of being rejected. But if we follow demographic parity here, we would have to select unqualified students from the demographic B, and that won't be a very good decision to make. So, coming to the third measure, which is equal opportunity. So, here, equalized odds takes care of both false positive rate and true positive rate, depending upon both the demographics. But what equal opportunity tells us, equal opportunity first identifies a preferred level, or it says that, okay, we will see, we this is the advantaged class, and we only want to look into that. So in doing so, if I just go to an example, it would be more easier to explain. Here I see they are only concerned about the qualified people and not about the unqualified people. So here the concept of advantage class. Here they are telling you are an advantage only like when you are qualified, and if you are qualified, we want to make sure that you have equal probability of getting selected. If you are not qualified, your probability of getting rejected might be different. So here, based on equality of opportunity, we see that irrespective of both the demographic, if you are qualified, you will have a 50% chance of getting selected. But if you are from demographic 1, you have a 70% chance of getting rejected. But if you are from demographic 2, you have a 90% chance of getting rejected. So that somewhat, so my equalized odd is not satisfied. Anyway, demographic parity is again not satisfied, but it is satisfying my equality of opportunity. So, given your problem statement, you have to decide like what kind of matrix do you want to use as a fairness matrix. So now coming to debiasing using adversarial training. So how do I train my model so that I can debias it? So let's say like I have trained a model, I have trained a classification model, and I have a matrix in my mind, and I have seen that okay, there is some kind of bias present. So I have to now debias it. So how do I do it? So here comes, so I will be showing how do I debias using adversarial training. What does adversarial training does? So I will go like step by step. So one, I have my input features, which is X, and I have my actual Y, and I have my predictor. So this predictor is nothing but a normal feed-forward network with a just like any neural network with a normal gradient descent, and I am predicting my Y. So my predicting my labels, which is like I will be predicting Y cap. So I want to make sure that my accuracy, whatever I'm predicting Y, should be somewhat equal to my actual Y. Let's say the weights are W. I am updating my weights W so that whatever Y cap I'm getting, my loss is minimized. But in doing so, I'm not taking care of the bias because I know after I have trained this model, I know that there is a bias present with respect to some protected variable Z. I'm not using Z as my input features. That is kept aside. So my protected variable Z is not part of my input features. So the protector has no idea about the protected variable. I mean, the predictor has no idea like what is the category of the protected variable for each and every observation. So now what I do, I have another my second model, which is adversary. What adversary network does? Adversary networks takes as an input my predicted levels, which is coming from the predictor, and it tries to predict the protected variable. So here, if there is a high correlation between my predicted Y and my predicted variable Z, then the adversary would perform really, really well. So what my predictor will do, the goal of my predictor is to prevent the adversary from predicting Z. So I have two networks. One is my predictor network and one is my adversary network. The adversary network is predicting Z given Y cap, which is the output of my predictor, and my predictor is predicting Y cap given the input and actual Y. But we have to now club them together. If we train them separately, then the predictor has no idea how the adversary is updating its weight U. Let's say the adversary has the weights U. Now the predictor need to know how is the loss. I mean, it has to stop the adversary from correctly predicting the Z. So in doing so, what we have to do, we have to transfer the loss into, so we have to somehow transfer the loss into the, while updating the weight of W. So how do we do that? Okay. So again, let's go one by one. Let's not go about how do we incorporate into like wise update the loss of the protected variable z. So what do I first do? I have my weights W and I am training my weights with this is so I am like updating my weights based on delta W L1, and L1 is my loss, while predicting the labels from input variable X and actual Y. And I have my weights U, and let's say while I'm predicting the protected variable Z, my loss is L2, and I am updating my weights U based on delta U L2. Now, this won't achieve me an unbiased model as I just said, because W has no idea how L2 is changing. So I have to make sure that I bring back the loss of that loss L2 in while updating W. So what would W want to do? The W should update itself in such a way that when the adversary is predicting Z, it should be very, very bad. So whenever the adversary is predicting Z in a very well manner, it should penalize the update function of the Y, update function of W. So let's see how it's happening. So it happens in like a two ways. So first we incorporate a negation of the delta W L2 in W's update function. So it's like, so what do I want to, so what do I mean by negation of delta W L2? So L2 is a loss coming from my protected variable. So till now what I am doing, I was only updating U. But now I want to see how should I change my weights W so that it increases my loss L2. So for predictor, I want to decrease my loss L1. Again, for adversary, U should be trained in such a way that L2 is decreased. But what again W wants? W wants the W should be changed in such a way that L2 is increased, because in doing so, it can make the adversary network perform very badly. That is its whole objective. Because if it's performed badly, only then it will stop predicting the protected variable properly, and we would be able to reduce the bias. So now my new update function becomes delta WL1, which is my update function from the predictor, and the negation of delta WL2. So, okay. But now there is one problem. The problem is it's possible that the way delta WL1 is changing, it is improving the accuracy by using the biased information. So what I have to do, I have to remove the component of delta WL1 by projecting it onto delta WL2. So what do I mean by projecting it onto delta WL2? It's nothing but I am removing the component of this one. So this delta WL2 have some kind of what do I say? Like it has a role in predicting L1, like it has a role in decreasing L1. What do I say that, okay, you just remove the component of delta WL2 from delta WL1. In doing so, I am removing any impact that the project protected variable Z had on predicting Y cap. So now when I train my adversary model, I will be, so this is my new update function for W. So I would be running, so for each and every iteration, I will be once running the adversary and once running my predictor using the loss function which is coming from the adversary. So that whenever the adversary is predicting, so that whenever is adversary is predicting good, I will make sure that with every training, it the L2 goes on increasing and L1 decreases. All right. So let us, all right. Okay. Let us see like the implementation code, like how you can implement, and how, if you like given a biased data set, how does the implementation looks like and how the end results looks like. So I had a public data set, and it had information. So this data set tells me a score test, like what is the probability that a person will be convicted again. So I have taken my sensitive, like a protected variable to be race, and I see that when I do a group by race and my score test, here one means that it will be that this person will be convicted again, and zero means it won't be convicted. So I see that African American has a 47% of conviction rate, like they have a 47% chance that they will be convicted again, and whether the Native American have a 37% of chance. And if I look at the other categories of race, they do have a very less percentage of chance as compared to these two racial categories. So I create my own variable because I just wanted to make it binary. So you can do it with multiple categories. Since I'm just showing a very small POC, so I made it a binary classifier even for the adversary. So what I did, I took, okay, if you're an African American and a Native American, I'm telling you X will be 1 and else it will be 0. And then I remove all the other sensitive information from my data set. I remove gender, race, scores because it's going into Y. So my Z, my protected variable, becomes my new race variable, which 1 means African American and Native American, and Y is my score test, 1 on 0. 1 means you will be convicted again, and 0 means you won't be, and Z are my all the feature space. I do have a lot of categorical variables. So to do a quick demo, I just did get dummies. I changed it into dummy variables. All right. Then I split it into train and test. What I also make sure here, I make sure that when I am dividing into train and test, I have 50% of my 50% of my population is from demographic like race 1 and 50% is from race 0. So in that way the data somewhat becomes balanced because both the race now have 50-50 occurrence in my data. And what I see like here, for even my train and test, my conviction rate is somewhat similar. So my samples are not very different from each other, my training and test samples. All right, so now what I do, I have to train two different models. So I will first train my two models separately. So this is my predictor network. So I am just using a two dense layer. So it is not a very optimized network. This is just a POC. So this is my predictor network, just a normal feed forward network. And here am I compiling the predictor network. And this is my adversarial network. And here I'm compiling the adversarial network. Let's just concentrate on this first. I have, and so what I do, so when I train my adversary network, so this is a function which says make trainable. This actually means it just says when you are updating W, make sure that you don't change. When you're updating U, please make sure you don't change the W, like you don't change the weights and biases in your predictor network. All right, so first what I'm doing, I'm training my predictor and adversary network separately. So I have my input shape, which is nothing but my X train shape, and for adversary input, my shape is equal to 1 because my output is just 1 and 0. So I'm taking my shape is equal to 1. And again, for adversary output, it is 1. And for my predictor output, it also be 1. So I'm compiling my predictor network here, and I'm also compiling my adversary network. So adversary network, my input is my predictor input, which is X, because the adversary, it will take the feature space and input. It will then use the predictor model to output Y, and then it will use that Y as an input to the adversarial network. So that's why when I'm compiling the adversarial network, I am taking my predictor input as my input, and I'm also taking my predictor model. But when I take this, when I'm training it, I will make sure that I don't change its weights and biases. So when I this function where it says I'm training my predictor and adversarial individually, and when I train my adversary network, I make sure that my predictor variable weights and biases are marked as false. That it won't be updated. You only update U and do not update W. Correct. So I'm just training it for like 30 epochs. It's like I just trained it for 30 epochs, and I just wanted to see how is my false positive rate changing from one demographic to another. So I had, as I told you before, I had two demographic groups, which I made one, which is the Native American and African American, and the other one is the which had a very low convection rate. Here I see my false positive rate for Z1, which is the sensitive category, is much higher than the false positive rate for Z equal to 0, which actually means the model is telling if you are from demographic, if you are from race 1, the model is giving, are penalizing them more, so it's telling, okay, you have a higher probability of getting convicted. And but if you are from the other racial category, the false positive rate is really low. That actually means, so there is a very like the bias is just very evident here. So what I do, I have to now train my adversary model. So in doing so, what I just explained, I have to make sure. So here, instead of now just training my predictor network, I have to train my predictor network along with my adversary. So where I will be taking into consideration the loss of the adversary into the predictor. So here I code my loss weights and I compile. So I haven't so this one. So the lambda, I haven't really played around with the lambda now. I just took 1 and -1. So lambda you have to is one of the hyperparameters that need to be optimized while training such models. Okay, so how do you train this? So first I have my predictor again, just like before, and I have my adversary, and I also have my predictor along with my adversary. So when I train it, I first train my adversarial network, and after that, so here you see, I'm putting like W is false. Do not update W. Only update U. After you have done this, what do I do? Now you update only W and stop updating U. But here you use the second loss function that we have just defined, which is the predictor along with the adversary. So this is, I just trained it for 10 epochs, and I just wanted to see how is my false positive and true positive rates changing from one demographic to another. So here I see for demographic 1. So my first part is when I'm not using the adversary network, when I'm just training my predictor. Here I see a very distinct difference from 13% and 6%, and for true positive rate here I see 59 to 36%. But when I come, like after I train my adversary network, I see my false positive rate for both the demographic are somewhat similar, and same with my true positive rate. So, okay, so right now the question will come about accuracy. So here, so this POC I just concentrated on the fairness and not about the accuracy. So the accuracy somewhat gets a little hampered when you train the adversary network, but it is more of a trade-off. So you have to figure out what kind of trade-off do you want in terms of accuracy and fairness. And also here I haven't done any proper hyperparameter tuning of the alpha, so the accuracy here is a little hampered. But the objective of showing this code and how it is working is more of showing that here we see that the false positive rate and true positive rate for both the demographics now are similar. So from a fairness standpoint, we have achieved a good fairness. Okay. So, all right. So this is it from my end. I would be happy to answer any questions.
Am I audible?
Yes.
Okay, so we have some questions here. Let's take first. So there was a Abhishek Thakur he says there was a study that revealed a racial bias in software used in healthcare industries. It was found that the software favored whites more than it came to a question like who would benefit the most most when it comes to extra medical care. How would you handle such a bias?
Can you please repeat the question?
Okay, so here it is. There was a study that revealed a racial bias in a software used in healthcare industries. It was found that the software favored whites more when it came to question like who would benefit the most when it comes to extra medical care. How would you handle such a bias?
Okay. So, so here what is question is, all right. So if you are a white, it's being said that you would require more medical care, and if you are a black, they are telling, okay, you do not require more medical care. All right. So here, if I look at my privileged group becomes okay. It should be like respective of your race. So it's like if even if you're a white or black, you should be, if you have a similar kind of disease, both of them should be qualified for, like, your percentage, the probability that a white should be given a medical care should be equal to the black. So I think it should go with the third one, which is equality of opportunity. So you want to make sure that whenever you train your model and you are using the fairness matrix, that the people who are so if like the people who have the similar kind of disease, irrespective of your racial status, your probability should be same.
Okay. So moving on to the next questions. Um, it has also been seen that there is a bias when it comes to people of color in many deep learning models used for project object detection. For example, a model recognizes an infrared thermometer as a gun when a person of color holding it. How can such bias be avoided?
All right. So I think this also becomes somewhat similar to what I have just told in
Yes.
the third example, that there was a kind of bias, like when so the dark skinned, whenever there was this dark skinned female, they were tagging them more as male instead of female. Again, like here, as you said, like a model is recognizing an infrared thermometer as a gun when a person of color holding it. So the bias is mostly present because of the so maybe the depending on the data you are training on, here they are seeing like most of the people who are from a colored background maybe hold a gun. So that's why even though it is not really understanding what you are holding. So it is just understanding, like, if you are a colored person, it is associating a colored person more with a gun rather than any kind of unsafe instrument. So,
Okay.
so the question with how can it be avoided. So again, like it can be avoided maybe two things. One, you can follow like one of the different methods that I just explained, or the another way will be making sure your data is balanced, the data that you're training is balanced. So if I have if my data set is such a way that I have a majority of my black holding a gun, anytime I give a picture with a black person with somewhat look holding something which not really like a gun or like holding something, it would associate it with a gun. So if you have a very good balanced data set where let's say a gun versus thermometer, like a 50% black people holding gun thermometer is somewhat same to like a same ratio to the uh, white people holding a gun and thermometer, it would be able to differentiate between a black person holding a thermometer, and it won't really tell like even if you're holding a thermometer, it won't tell like it's a gun. It won't associate like a gun and thermometer with your colored holdings.
Okay. So no more questions are here. So I guess we can end our session now. Am I audible?
Yes.
So thank you, Debasmita. Thank you for accepting our invite. The session was okay. Okay, there's one question. Uh, can you try to give an intuition on how the data can be biased when the data we use for training is completely balanced? Do we have to spend more time in understanding the statistics in the data first?
Okay, so I mean, if your data is if your training set is completely balanced, I don't think there can be bias when training your AI model. So, for example, if I take the example of the male versus female candidates, the bias arises only because the number of male candidates present in the data was much higher than the female candidates, and the conversion rate of the male candidates were much higher than the female. So that from that standpoint, my data set wasn't biased at all. But here you're saying that your data is completely balanced. So if your data is completely balanced, then I'm not sure how. I mean, maybe here there is like really less chance that there will be some kind of bias while training a very balanced data set. I mean, you can try and check the different fairness matrix to see if it is coming up with coming like giving you any bias while you're training it. But if your data is completely balanced, then maybe your training won't be biased.
Okay. So moving on to next question. Here we have is um, he's asking how to decide like evaluation of GANs and when should we use them.
Okay, yeah. So it is using an adversary network. It is somewhat equivalent to the GANs, the way the GANs work, which is more of here the generator. It's equivalent to the predictor, and the discriminator is the adversary network, which we were training. So it's not the only way of mitigating bias. Like there are other ways of mitigating bias also. For example, there is one way of mitigating bias is like where they try to you have this unbalanced data set and where they try to change some of the labels and try to balance it before training. I forgot the name of the paper, but what they are doing here is they try to find out. So they do rank it. So let's say I have different categories. Let's say race one and race two, and I have y equal to one and y equal to zero. We try to figure out given race one, which is the privileged class, what is the what which one is the least observation that should not have been selected. So, like if you are from a privileged class and your y is equal to 1, we take that and see out of them, if we rank them and we see that which one have the lowest probability of getting selected. So we then say, so we change my data set. I change my y. I make them that, okay, if you have a lowest probability of getting selected, why don't I just make you y equal to 0 instead of y equal to 1? So we do some small changes in my training set itself, and then we try to make it balanced, and then we train my balanced data set. So, but if you want to use adversarial training like this, then it could be some similar kind of GAN implementation.
Okay. So next question we have is, should adversarial network and predictor network be trained simultaneously or one after another?
It shouldn't be trained simultaneously. It should be like one after another. So I first train my predictor and adversarial separately, one after another, and feed them. And afterwards, what I do for each and every epoch, I train my adversary once. Then I take the loss as an input into the predictor, and then I update my y. And like that, the iteration continues.
Okay. So no more questions are here. I guess we can end our session now. Thank you, Debasmita, for accepting our invite. Session was very amazing. Thank you everyone for watching. Thank you. Keep supporting.
Thank you.